Now we will discuss the optical properties of colloidal solutions, right? To understand the optical properties of colloidal solutions, we would be performing a simple experiment, and in this experiment we would be taking these two containers. One contains a true solution and another contains a colloidal solution, right? And these two containers are kept in a dark room, right? And we'll pass a beam of light through these two solutions, right? So when a beam of light is passed through true solution and a colloidal solution which are kept in dark room, it is observed that the beam of light illuminates with a bluish light in case of colloidal solution, whereas no illumination is observed in case of true solutions, right? So I'll repeat a simple experiment where you take true solution and a colloidal solution. You keep these two containers in a dark room, right? And a beam of light is passed through these two solutions, right? And it is observed that true solution would be illuminated by a bluish light. This colloidal solution would get illuminated by a bluish light, whereas no color is observed in case of true solution, right? So there is no illumination in case of true solutions, right? So we'll just write down the observation. Path of light gets illuminated by a bluish light in colloidal solution and no illumination is observed in true solution, right? Now what could be the reason that you see the beam of light gets illuminating with a bluish light in case of colloidal solution, whereas no light is observed in case of true solution? What could be the reason? Now let's see that. We know one point of difference between a true solution and a colloidal solution is that the particle size, right, in case of true solution is smaller as compared to colloidal particles, or as compared to the particles in colloidal solution, which are dispersed phase particles, right? And particle size in case of true solution is less than 1 nanometer. We have done this in our previous lectures. And particle size in case of colloidal solution ranges between 1 nanometer to 1000 nanometer, right? So here particle size is bigger compared to true solutions, right? So particle size in case of true solution is less than 1 nanometer, right? And in case of colloidal solution it's between 1 nanometer to 1000 nanometer, right? So particle size in case of colloidal solution is bigger, right? Is bigger compared to true solutions. So what happens is, when the beam of light, right, will strike a particle in colloidal solution, it will get scattered, right? The beam of light, right, suppose these are the particles in case of true solution. So when this beam of light will strike with the dispersed phase particles in colloidal solution, this light will get scattered, right? If it will strike with this particle, this way light will scatter, right? So there is scattering of light, right, in case of colloidal solutions, right? And scattering is due to the dispersed phase particles, right? But we have particles in case of true solutions also, right? Then what happens? Why we don't observe any color in case of true solution? It's because, as I said, that particle size is less than 1 nanometer, which is too small for light to scatter. Due to very small size of solute particles, in case of true solution, the light won't get scattered, right? So due to small size of particles in true solution, light will not get scattered. Beam of light will not scatter, right? Whereas the particle size in case of colloidal solution is big enough to cause the scattering of light, right? And dispersed phase particles are big enough to cause scattering of light, right? And it is due to this scattered light that we see the illuminated path in case of colloidal solution. And as I said here, that path gets illuminated with a bluish light, right? So you will observe different colors in different colloidal solutions, and this color depends on the wavelength of the light that gets scattered, right? This different wavelength gets scattered, right? And the color of the solution depends on the wavelength of the light that gets scattered, right? And wavelength VIBGYOR, if you remember this with GYOR, we have done this in our previous classes also, and in this direction the wavelength denoted by lambda increases, right? So more is the wavelength, less is the frequency, right? So here frequency in this direction decreases and in wavelength increases. So blue light has less wavelength, right, compared to red light, right? We'll be using this in a moment. So now it is clear that why do we observe color in case of colloidal solution? It's due to the scattering of light by colloidal particles, and this scattering of light by colloidal particles is known as Tyndall effect. This is your Tyndall effect, right? So this is what is the important thing in optical properties of colloidal solution, Tyndall effect, right? So Tyndall effect is important and is due to the scattering of light by colloidal particles present in colloidal solution. So this is your Tyndall effect. Tyndall effect. Why we call it Tyndall? The Tyndall effect because this was observed first time by scientist Tyndall in 1869. So in his honor, this effect is known as Tyndall effect, right? This is observed by Tyndall in 1869. So we call it Tyndall effect, and Tyndall effect is scattering of light. What is this effect? Scattering of light, right? Scattering of light by particles of colloidal solution, right? This is your Tyndall effect. Scattering of light by colloidal particles, let's write it as colloidal particles, or we also call it as dispersed phase particles, right, in case of colloidal solutions. In colloidal solutions, by colloidal particles in colloidal solutions, right? And this effect, I'll repeat, scattering of light by colloidal particles in colloidal solution is your Tyndall effect, right? And this cone of light, if you observe, this is a cone of light. This cone of light is known as Tyndall cone, right? We call it a Tyndall cone. Right? Since this is in the shape of cone, so we call it to this beam of light passing through this colloidal solution, we call it a Tyndall cone. Right? And okay, now let's come to this. The wavelength of light that gets scattered, right? And it's due to this wavelength of light that we observe different colors, right, of colloidal solutions. So the light that gets scattered, right, by colloidal particles depend on the size of the colloidal particles, right? Because we know that size of the colloidal particles ranges between 1 nanometer to 1000 nanometer. So we have different range of particle size in colloidal solutions, right? And if we recall, we have, I'm sorry, no, we have not done this before. Okay, if we look at the colloidal solution of silver, right, silver sol, and if you pass light, right, through silver sol, if you perform the same experiment using silver sol, we observe different colors, right? For silver sol, right, if you pass beam of light through silver sol, you will observe different colors. Orange, you observe orange, red, orange, yellow, right, purple and violet. You observe orange, yellow, orange, red, purple and yellow, right? These are colors observed when a beam of light is passed through colloidal solution of silver. And why we observe different colors? I said that the color of light, the color of light that is observed is due to scattering of light, right? And scattering of which light gets scattered, the wavelength of light that gets scattered gives you the color of light, color of colloidal solutions, right? So here all these colors have different wavelength, right? And light of different wavelength is getting scattered due to difference in particle size of colloidal solutions. If you look at the particle size, it's 6 into 10 to the power of 15, 6, 9, it's 6, 9, 13, 15, all 10 to the power of minus 5, 10 to the power of minus 5, 10 to the power of minus 5, 10 to the power of minus 5 nanometer, right? Since the colloidal sol contains these range of particles, right, it's mm, right? Colloidal solution of silver contains these range of particles, right, different size of particles. So when a beam of light strikes these particles of different sizes, the wavelength of light, right, that gets scattered would be different depending on the size of the particles, right? So here wavelength, so the light scattered depends on the wavelength of light, right, or the light that gets scattered depends on the size of the particle, right? So the wavelength of light that scatters, right, depends on the size of colloidal particles, right? So we have different sizes of colloidal particles, so the light that gets scattered would be of different wavelength, and different wavelength means different colors. So that is the reason. I'll repeat, this is important, right? You have a silver sol. If you pass a beam of light, you will observe different colors, right? And these are the colors that you observe, right? And we know that the color of colloidal solution is due to the scattering of light, right? And the color depends on the wavelength of light that gets scattered, right, by the particles of different sizes in colloidal solution, because the wavelength of light that scatters, right, depends on the particle size, right? Different particle size will scatter light of different wavelengths, and depending on the wavelength of light that gets scattered, you see the color of colloidal particle, the color of colloidal solution, right? I hope now it's easy. So I'll just note it down here that the color of, let's use sol, color of sol is colloidal solution. Color of sol depends on the wavelength of light scattered, right? Wavelength of light scattered, and the wavelength of light that gets scattered depends on the size of the colloidal particles, and different sizes of colloidal particles scatter light of different wavelength, due to which you see different colors, right, of colloidal solutions. So color of light depends on the wavelength of light scatters, which in turn, that is the wavelength of light scatters, which in turn depends on the size of colloidal particles, right? So this point is important, and this is the experiment which proves this point, right? So I hope this is clear to you, right? So now, based on this, we have one more thing. We know that in physics you might have read Rayleigh scattering, right? And as per Rayleigh scattering, the scattering of light is inversely proportional to the fourth power of wavelength, right? Scattering is inversely proportional to the wavelength of fourth power of wavelength of light, right? So here, if you now look at this Vikrant, right, this blue color has less wavelength compared to red color, right? So since scattering is inversely related to wavelength, so blue color or this blue in Vikrant has less wavelength, so it has less wavelength, so scattering would be maximum in case of blue color. And if you talk about red, since red has maximum wavelength, so scattering would be minimum, right? So based on Rayleigh scattering, we say that blue color shows maximum scattering, and red color shows minimum scattering. It shows minimum scattering, and it is due to this reason that in the clear sky, right, when the sun rays, right, reaches us, the sun rays in air get scatters, right, by the colloidal size particles of air. Air contains dust, right? So the dust particles is of colloidal range. We know that it's the dust particles that are in air, right? The dust particles of colloidal range, which falls in this range, will scatter light, right? So here the scattering is maximum for blue color, right? So that is why the color appears blue to our eye, right? It is due to, because we know that what we see, right, the color that we see is due to scattering of light, right? So when the light of sun, right, travels in air, it will scatter the light, right? It will scatter the light, and as per this relation, the scattering of light would be maximum for blue color. So that is why that is why the sky appears blue to our eye, right? It is due to the maximum scattering of blue color based on Rayleigh's relation. Scattering is inversely proportional to wavelength of fourth power of wavelength, right? I hope this is clear to you. So blue color shows maximum scattering and red color shows minimum scattering, right? So due to this, the sky appears blue in color due to scattering of light, white light, by dust particles which are in air of colloidal size, right? I hope this is clear. Now there is a simple experiment again, right? This same Tyndall, this is your ultra microscope, the arrangement that you see, right? This arrangement is that of an ultra microscope, right? I forget to write. This arrangement is that of an ultra microscope, right? Ultra microscope is different from a normal microscope in that the light enters laterally, right, in ultra microscope, because in normal microscope light enters from below, right? So this is the simple experiment of ultra microscope, right? And in this experiment what we would be doing is an intense beam of light, right, would be sent through the liquid under study in the darkened space. This is again, we would be doing this in a dark room, right? And this is the liquid under examination, which is a colloidal solution, or it's a solution, right, which is kept in a dark room, right? And when it is viewed under a powerful microscope, right, directed at right angles, this is the beam of light, this is an arc lamp from which a beam of light will pass, and these are two lenses, this is a slit, right? So when a beam of light will pass through this test solution, right, this is a test solution. When a beam of light is passed through this test solution and you observe this solution in this, under this microscope, under this powerful microscope that you see at right angles to this beam of light, it is observed, you will, in this microscope you will observe some luminous points, some bright points, right, with in a dark background. The observation in this powerful microscope when a beam of light is passed through this test solution would be that in this microscope you will observe some bright luminance points, right, on a dark background, which is due to the scattering of light by colloidal particles, right? Here, since this is a colloidal solution, so the particles in colloidal solution will scatter the light, right? So when the light will get scattered, right, when you are observing through this powerful microscope, so the scattered light will reach the observer's eye, right? And it is due to this scattered light that you see some bright points on a dark background, and right, and those dark points are due to those colloidal particles, right? So you can see the number of particles, right, but you would not be able to determine the size of those particles, right, because you just see some in this powerful microscope. If you will see some bright luminance points on a dark background, right, which is due to the scattering of light, right, by the particles of colloidal range. And if you take, instead of colloidal solution, if you take a normal solution, then nothing would be observed. You will just see dark, right, in this powerful microscope, right, which is placed at right angles to the beam of light. This microscope is at right angles to the beam of light, right? So nothing would be observed, or just a dark background, just a dark thing would be observed in case of true solution. whereas in case of colloidal solutions you will see some bright points, bright luminance point on a dark background, right, which is due to the scattering of light. The light that the colloidal particle scatters will enter the observer's eye and he will observe those bright points, and those bright points are nothing but they are colloidal particles that are scattering the light, right. So I hope this is clear. So this is an ultra microscope which is based on your Tyndall effect, right, Tyndall phenomena. Right, so it is only light scattered by colloidal particles and actual particles are not visible, right. So what you are observing is the scattered light due to those particles. So these bright points that you see, these are not particles, but it is due to the scattering of light by those particles. So it is the scattered light, right. So I hope all this is clear to you. This is important. It has many things. You can just take all these things down. Remember this Rayleigh scattering, why the color of the sky appears blue, right, because blue color has maximum scattering, right, because its wavelength is minimum, right. And here why we see this color in case of colloidal solution, it is due to the scattering of light by particles of colloidal range, right, and this effect, right, wherein the colloidal particles are scattering light, this effect is known as Tyndall effect, right, scattering of light by colloidal particles in colloidal solution. And color of solution, this color depends on the wavelength of light that gets scattered, and the wavelength of light that gets scatters depends on the size of the particles, right, due to which in case of silver solution you will see multiple colors, because the silver colloidal solution contains dispersed particles of different sizes which is in colloidal range, right. So different particle size will scatter light of different wavelengths, due to which you will see all these colors, right. I hope all this is clear to you. Thanks.